Okay, okay. So today we're very happy to have Kumar Murty of the Fields Institute and the University of Toronto to speak about Non-vanishing of Poincare series.
Okay, thanks, Payman. So it's a bit weird. I'm one of the supposed to be one of the organizers of this.
That's why I was smiling.
Yeah. So the only reason the organizers speak is when you couldn't find a speaker.
When a speaker cancels, and then
right, that's right. So I thought I'd talk to you about some work that is in progress with Manikyam and Ramakrishnan. Both of them are mathematicians in India. Ramakrishnan, at least until recently, was at the Harishchandra Institute in Allahabad, and Manikyam was at the Kerala School of Mathematics, but I think he's retired recently. So he and the three of us have been talking about various problems in both the classical and modern theory of modular forms for some years. And this is some work that we started a while ago, and I thought maybe now if I give a talk about it, it'll induce me to finish it. So let's go back to a classical problem involving the Ramanujan tau function. So here's the Ramanujan cusp form, delta z. We call it the Ramanujan cusp form, but of course delta of z was studied as a automorphic form by Dedekind, and so earlier than the Ramanujan. Ramanujan's main contribution, I would say, is to multiply out the product and then realize that these numbers that you get here are extremely interesting integers. And maybe the whole modern theory of Galois representations and congruence properties of modular forms and the reciprocity laws that modular forms, automorphic forms contain was born from that. So it's really quite an amazing idea to see that this sequence of integers would be so profoundly important.
But anyway, sorry to interrupt. A couple of people in the chat box are asking if it would be possible to make it a little larger.
Okay, sure, we can try that. How though? Let's see. I've lost the. There it is. Okay. So let's see. What if I?
Yes.
Then how do I increase the boundary of this thing? Like, can I make this boundary bigger? Can I make it full screen or anything like that?
That I don't know, unfortunately. Maybe someone else can help.
Right now, it already looks like full screen, and we can see it much better now. So
okay.
If it's okay for you, it's good for us.
Yeah, it's okay. Okay, so I'll put it as much as it can fill up the. Yeah. So there are all sorts of important aspects about this tau function that have been discussed in various other ways, but also afterwards other problems were raised by various people. And famous problem is of Lamer, who said in the 40s, asked in the 40s whether this function can ever vanish. And his conjecture was that it never vanishes. Tau n is never zero for all n bigger than equal to 1. This problem is still open. I call it Lamer's conjecture. And a lot of people have thought about this from various points of view. So computational people have been chugging away, and there's this number that I can't even pronounce. So we know that the tau function doesn't vanish for any n up to this number. And this is even not the latest result. This is 2013. So maybe we've gone beyond that. But as far as numerical calculations show, it seems to be holding up. Now, one important point is, though Lamer is asking about the non-vanishing of tau at integers n, in fact, it suffices to show that it doesn't vanish at prime arguments, and the proof is pretty simple, given the properties of the tau function, because the tau function is multiplicative, and so if tau of n is 0, then writing n as a product of prime factors, one of the factors has to be 0. But now here's a little bit of this part is a little less trivial, that if tau of p to the alpha is 0 for some prime p, then in fact tau of p has to be 0. And to see that, we know from the Ramanujan hypothesis that tau of p can be written as a sum of two complex conjugate numbers, each of absolute value p to the 11/2. Call it pi p, and pi b bar is the other one. Then by the recursion formula for how you compute tau at a prime power argument from tau time argument, you have this kind of formula. That is tau of p to the alpha is pi to the alpha plus 1 minus pi bar to the alpha plus 1 over there. Now notice this denominator is not 0, because if pi p is pi p bar, then from here, it follows that lambda has to be plus or minus 1, because lambda bar will be equal to lambda, and absolute value of lambda is 1. But in that case, tau of p would be 2 times pi p, and that's not an integer. So this denominator is not 0. So this makes sense. And now if tau of p to the alpha is 0, that means that the alpha plus first power of pi p is the same as the alpha plus first power of pi p bar, which means that pi p bar is a root of unity times pi p, where in fact it's an alpha plus first root of unity. Okay. But now you know that zeta is in the field generated by pi p, because pi p is this is at most a quadratic field. Pi p and pi p bar satisfy an equation with integer coefficients. So this is a quadratic equation with integer coefficients, and so this is a quadratic field at most, and in fact exactly is. But anyway, zeta by this relation here then would have to belong to that field. So this quadratic field has a root of unity. So quadratic fields only have roots of unity of order 2, 4, or 6. So zeta has to satisfy one of those. Okay. And moreover, if you look at the relationship between lambda here, lambda and zeta, what you get is that lambda bar is zeta lambda. So that means that zeta is lambda to the minus 2. And so therefore lambda is also a root of unity. Remember again, what is lambda? Lambda is this, this constant here. So lambda is again a root of unity. Okay, but then lambda squared is zeta, so therefore lambda generates a field of degree at most 4. But now if you look at what is then tau, the formula for tau of p, it's pi p plus pi p bar, which would be 1 plus zeta times lambda times the 11/2, and that's an integer. And now if this is not 0, then in particular zeta is not minus 1. But then that means that root p is in the field generated by lambda, right? Because zeta is in the field generated by lambda, and rest of this is an integer. So root p would be in the field generated by lambda, but that's a field which is lambda is at most, a 12th root of unity, and so this is unramified outside of 2 and 3. So therefore p must be at most 3. But then it's easy to show. I wrote down here tau of 2 and tau of 3 are not 0, but in fact you can show by just by bare hands that tau doesn't vanish at any power of 2 or any power of 3. Okay, so therefore the only way all of this could work is the zeta in fact had to be minus 1 and tau of p is 0. So Lamar's conjecture then, to prove it, all you need to do is show that tau doesn't vanish at any prime argument. Now there we have, because of Galois representations in Chebotarev density theorem, one knows a lot about how to count such occurrences if they occur at all. And we know, assuming nothing unconditionally, that it's the set of primes where tau p vanishes is density 0. So there's a it's bounded by x over log x to the alpha for some alpha bigger than 1. And if you assume Riemann hypothesis, you can get a sharper bound like x to the 3/4. I don't think these methods are likely to give x to the half. And on the other hand, we expect this set to have cardinality 0, that to be an empty set. So this method is not going. I don't think it's going to solve Lamar's conjecture, but it's an interesting fact. Now here's another interesting, slightly curious point about Lamar's conjecture. He says that tau of n is never 0, but to prove it, it'll be sufficient to show that the set where it vanishes has density 0. They're equivalent. Certainly, of course, if it never vanishes, then this set is density 0. But conversely, you see, if you had some n for which, if this suppose this set is density 0 and it was non-empty, so there was an n such that tau of n is 0, then by the argument we just made, tau of p has to be 0 for some prime p. But now take any integer which is only divisible by p to the first power. and then tau of that is 0. So, well, the density, that's a set of positive density. The number of integers which are divisible by prime only to the first power is roughly like that. So that's the set of positive density. But you know that the hypothesis is the set of n's where it vanishes is density 0. So it's a curious thing, just I mean, not hard to see, but until it's pointed out, it may not be obvious. Whether you prove it never vanishes or whether you prove that the set where it vanishes has density 0 is the same. Now, as is well known, delta is a modular form of weight 12 for SL2Z, for the full modular group. And we can now abstract this question of vanishing of these Fourier coefficients to a question involving other cusp forms, in particular to Poincare series. So what is a Poincare series? They are indexed by weight and an integer n, and these are like sort of like Eisenstein series. You can construct these cusp forms on more quite generally, in fact. And so for SL2Z, it looks like this. You go over matrices in SL2Z with where you only care about the bottom row. So you go over the bottom row, so to speak. And then it's e to the 2 pi I m gamma z over cz plus d to the k, where gamma z means if this is a, b, c, d, az plus b over cz plus d. Now, of course, there's more than one matrix in SL2Z with the same bottom row, but the point is any two of them will differ by a shift by an integer, and so it won't make any difference for this exponential factor. So another way of writing this is you can go over SL2Z cosets for gamma infinity, that is the stabilizer of the cusp at infinity, so the mod out by the unipotency. Okay, so for k bigger than 2, this series converges absolutely and uniformly on compact sets. And notice, by the way, that we know that for SL2Z, there are no modular forms of weight less than 12. And so you're going to get, these could be 0. These could give you 0. Okay. So for n bigger than 0, this is in fact a cusp form, and it has a well-known Fourier expansion. So people have worked this out in great detail. I probably get it wrong, but anyway, it looks like this, that if I write this as am e to the 2 pi m z, am is given by an infinite sum, which involves some simple factors, but then two very important factors. One is a Kusterman sum, and one is a Bessel function. Okay, and these Kusterman sums, of course, are arithmetically very interesting. They've been studied for a long time. In some sense, they've been, you think of them as kind of not Fourier coefficients, but maybe eigenvalues for actions of Frobenius on certain sheaves. And you can, yeah, so therefore you can learn a lot about the Fourier coefficients of this by explicitly working with this description. Now, Poincare series are important or interesting for the following fundamental property. I mean, they're interesting for many reasons, but maybe in this context, they're important for the following important property: that if I take the inner product of a Poincare series with a cusp form, the Peterson inner product, if I take the inner product of f with the nth Poincare series, I get essentially the nth Fourier coefficient of f. Okay, normalized by some stuff here. So if I write out the Fourier expansion of f at the cusp by infinity, then I can get these Fourier coefficients by taking the inner product with the Poincare series. And in particular, if you apply this to k equals 12, since the weight 12 cusp forms is one-dimensional and generated by delta, each one of these for each n is a multiple of delta. Okay, and moreover, because of this fact, the vanishing of tau of n is the same as the vanishing of the Poincare series. So now, more generally, we can replace Lamar's conjecture with the question of non-vanishing of Poincare series. see we take a sort of one step towards making this a little bit more conceptual. I'm sorry, I don't know how to stop. I get a constant deluge of email. So every time I get email, this program makes a noise, and I don't know how to turn it off. other than to completely shut down email. Okay, so now some years ago, Rankin looked at this problem of non-vanishing of Poincare series. Here's the first observation. So the space of cusp-forms of weight k for SL2Z as dimension roughly k, instead of k over 12, roughly speaking. And so if I take the first, let's call this dimension d, the first d Poincare series, then they've got to span the space. In fact, they do span the space of cusp-forms, and therefore none of them can be 0. Okay, so it's known that the first d of them, where d is a dimension of the space, span the space as k, and therefore none of them are 0. Okay, so since d is roughly about k, but what I'm saying is that we already know, roughly speaking, the first k or k over 12 of them are non-zero. Okay, what Rankin showed is that this can be extended roughly up to k squared. So let me see. Rankin showed that for k sufficiently large, I can go for n up to just shy of k squared, and these Poincare series are not 0. So you got some absolute constant b here, and this is k to the minus epsilon. So it's just short of k squared. And he does that by really digging into the Fourier coefficients, the Fourier expansion of the Poincare series, and does a very subtle estimation of Kloosterman sums. So what I want to talk about is, as I said, work in progress with Manikyam and Ramakrishnan, where we take a completely different approach. And we're going to try to show that the Poincare series are non-vanishing. And so far, the results seem to be that we can go up to gamma of k over 4. So roughly an exponential improvement of Rankin's result. Yeah. So let me try to see if I can explain or motivate, or no, I don't know if I'm motivated, but I can sort of tell you. So, and as I said, our approach is completely different. We're not looking at subtle estimations of Kloosterman sums. So rather, we're going to use something called the Conan kernel function. So this was introduced by Conan in 1997. And what it is it's some decoration here, but then sum over A, B, C, D in SL2Z, CZ plus D to the minus K, AZ plus B, or CZ plus D to the minus S. So you have two variables, K and S. And what you show, I mean, if I write this in the correct way, and rather than explicitly, if I actually show you that in fact it is on the function z to the minus s, acting by elements of SL2Z, you see that is automatically an element, it's a cusp form. And like Poincare series, that the inner product of the Poincare series with other cusp forms gave you the nth Fourier coefficient. This one has the property that inner product with other cusp forms gives you the L function. Now it's the decorated L function. So in other words, it's the full. In other words, it's So if I have this is the Fourier expansion at infinity, then I take the Mellon transform, I get this Dirichlet series, and then L star means I've added the exponential term and the gamma factor. Okay, so up to a constant C sub k, which is given explicitly like this, it's about pi and power of 2 and a factorial involving k. I basically pick up the L function. Okay, it's a very interesting property of this kernel function. Its inner product with the f gives you the L function. Okay, well that means you can do a lot of things with this. You can play a lot with this. Okay, so what do we do? The first thing you can do is see if you can use it to prove non-vanishing of L functions. So this is in fact what Conan did with it. So to do this, you need to understand two different sides of the L of this kernel function. One is the spectral side. In other words, how do you decompose it in terms of cusp forms, and second thing is the Fourier expansion. So as I just said, because of its inner product with the modular form gives you the L function, you can express this kernel in terms of Poincare series. Well, it's a cusp form, so you can write it in terms of Poincare series, and then you show that the first Fourier coefficient is non-zero to deduce that this other expression in terms of L functions also has to be non-zero. Okay, let me say that, maybe I say that more clearly again. On the one hand, this cusp form can be written as its spectral decomposition involves these L functions. Okay. On the other hand, you can expand it. You can work out the Fourier expansion in terms of Poincare series, and if you show that, and if you compare the first Fourier coefficient on both sides, then you get that this thing is equal to the first Fourier coefficient on the other side. And if that's not zero, you get this is not zero. And which values of S does this work for? Just off the critical line. So remember, the weight k, so the critical line is k over 2. So as long as I stay a fixed amount to the right of k over 2, and k is sufficiently large, depending, unfortunately, on the imaginary part and on delta, then I get this is not zero. So in a way, you can think it's a kind of Riemann hypothesis. Right? The catch, though, is that how big k has to be depends on the point I'm trying to prove non-vanishing for. I don't have a uniform estimate. Okay, so this is a really very interesting thing to this has a lot of consequences. That it's sort of, if you give me a point in the critical strip which is not on the critical line, then for sufficiently large weights, this thing will be non-vanishing at that point. Okay, and sum is over a basis of normalized eigenforms. Now, some time ago, I worked with Manikyam, the same Manikyam, and as one of the co-authors of this work on Poincare series, and his student Sandeep. Sandeep is a very bright young man. He's just graduating. He's on the job market this year, so if you have positions, you might look out for him. Oops, it keeps dropping. I hope we're going to make it through this talk. Yes. Okay. Okay, good. So what did we do? We rather than evaluating the Fourier expansion, we considered the function at a point z equals I and real point. So remember, what do we have? We have this kernel function. When you write it in terms of the basis of cusp forms, the inner product involves the L function. So basically, you get a linear combination of the L function times F. Now I can evaluate, that's a function of Z on both sides. So I can evaluate that at Z equals I. And you take for S a real point sigma. So you look at this kernel function at I. Then what we did was we actually tried to establish the asymptotics of this, and this is what it looks like. It behaves like 2. And this allowed us to deduce then that for a given sigma in the critical strip, a real point in the critical strip, there's an eigenform F satisfying LF sigma is positive. And moreover, you can use the same thing to get not only positive, but you can get a lower bound for the absolute value. Not a very strong lower bound, but you get a lower bound. Okay. So this bound is weaker than what we may expect, but if we weren't looking for the optimal lower bound, we're just trying to show that there is more information in these kernel estimates than has been used so far. Okay. Now, more recently, we extended this a little bit. More recently, we extended to consider the asymptotic growth on the imaginary axis. So here we had just looked at the point I. Well, now you might as well look at IY and let y go to infinity. So we did that. And what you get is a rapidly converging infinite series plus a very good error term that looks like this. Okay. And now, of course, you know why I want to take IY, because what do I have? This kernel function looks like the L function of f times f at the point z, IY, right? So now if I take the Mellon transform, if I integrate over y, I'm going to get two L functions. So what you get is you'll now get an expression for a product of two product of the L function at two different points, rather, not two L functions, product of the L function at two different points. And using that, we're able to remove the absolute value sign on this, and you get that there is an L function given a point sigma in the critical strip. You can find an f such that LF sigma is bigger than this bound, and this requires k to be sufficiently large, bigger than sufficiently large, dependent on delta. And as I said, by taking Mellon transform, you also get results on the growth of the L function of f evaluated at two different points. Now, this can be used to get simultaneous non-vanishing at 2 points. So if I have 2 points S and W in certain subsets of the complex plane, then you can try to you can show that for at least k to the epsilon of the forms, both the L function doesn't vanish at both of those 2 points. And what are these shapes look like? Well, they're kind of weird shapes. I tried to draw one here. That's the explicit description, and you get shapes. These are I mean, this is in the complex plane, so you can't really draw it, but I took this real parts, and you get some domains like this where you can show these kind of simultaneous non-vanishing. Okay. And from that, you can deduce a couple of results. You can deduce that you can deduce theorems about the number of f's which don't vanish at a given point. Remember, before we got that non-vanishing at the existence of an f, that's the non-vanishing at a certain point. But now with these two, the L function evaluated at 2 points, you can actually use it to get a bound for the number of f's where the L function doesn't vanish at the point. And it's still, I would say, a weak result, but it's non-trivial. We have k to the half plus sigma minus k, a little bit like k to the half minus delta. And S is constrained to be in a certain rectangle in the critical strip. So about delta away from the boundaries k over 2 and k plus 1 over 2. The edge of the critical strip is k plus 1 over 2 in the sense of absolute convergence. Okay, so beyond the results themselves, the point is our approach is very different from what there's a lot of papers, by the way, in the literature of people trying to deduce different consequences from different applications of Conan's kernel function. And I think our approach is completely different from all of those. We actually used a technique developed by another Rankin and Swinnerton Dyer, when they were looking at zeros of Eisenstein series. That's the technique we used to get the asymptotic, this asymptotic here. This kind of asymptotic here, this kind of asymptotic here, and also the earlier one I said here, this one. We used the method of Rankin and Swinnerton Dyer on zeros of Eisenstein series. And what it does is it allowed us to decompose the kernel function into different kinds of pieces and identify the part that makes the most significant contribution to the growth. Okay. Now, as I said, there are lots of papers in the literature where people have looked at either applications of Conan's kernel function or related results. In particular, the theorem of Luo that uses mollifiers to show that, in fact, a positive density of the f's have the property that the critical central critical value is not 0. So that's a completely different method. You compare the first and second mean, but you have to introduce a mollifier. So for those who know, this mollifier is like a Dirichlet polynomial which approximates the inverse. And that's a common technique that you use at when you want to show count number of non-vanishing rather than existence of non-vanishing, you introduce those kind of polynomials. And he showed it works quite beautifully here, and he got that a positive proportion or non-vanishing. Then there's a paper of Sengupta who used the Fourier expansion of the kernel function to show the Lindelof hypothesis implies a lower bound of k to the 1 minus epsilon for the number of these f's where the L function is positive. So our result was unconditional. We didn't use Lindelof hypothesis, but of course our bound was weaker too. But then more recently, there's a paper of Choi, Konen, and Zhang, where they use similar methods to study simultaneous non-vanishing of an L function at 2 points. You can see it's set up to do that. It's not that's sort of what you might expect to be possible. And then a paper of Kuri, Makdisi, Koner, and Raju, who they give an expression for the Mellon transform of this kernel function in terms of gamma functions and hypergeometric functions, and again use it to deduce simultaneous non-vanishing. In these two works of Choi, Konen, and Zhang, and Kuri, Makdisi, Konen, and Raju, again the emphasis was on showing existence of cusp forms whose L function has simultaneous non-vanishing. While as in this work, it is these two works, it's about counting the number of them. So in our work also, it's more about counting the number. Okay, so now that's sort of a long-winded introduction, but to come to the subject really today of Poincare series, the point is we start again with Conan's kernel function, but now we introduce a variation of this, kind of a twist of it. So what you say is that take a prime L and take a non-trivial character, Dirichlet character mod L. And then I will consider, so in Conan's L function, kernel function, I had that CZ plus D to the minus K, and then I said AZ plus B over CZ plus D to the minus S. What I'm going to do is I'm going to translate this by a rational number, V over L, and I'm going to twist this by a character, chi bar of V. And I'm going over the ABCD in SL2Z and V mod L. And lambda is a constant, or not constant, it's an explicitly defined function. Okay, so the conditions on S, namely that the real part between 1 and K minus 1 and ZB in the upper half plane means that you have absolute and uniform convergence on compact sets. Now let's just see what is the spectral decomposition of this. Before, remember, we got nicely the L functions. So here what happens is, if you start from, let me say how you do this. We start from a well-known formula because it's part in complex analysis, maybe so-called Lipschitz formula. So if sigma is a real number bigger than 1 and Z is in the complex upper half plane, then 1 over Z plus N to the S, when you sum it up, can be written in this form, n to the S minus 1 e to the 2 pi I n Z. Because Z is in the upper half plane, this converges nicely. Now, if I take Z and replace it by this rational translate, okay, I get something similar, but now because I've moved Z a little bit, I get this root of unity sitting here, e to the 2 pi and V over L. So now let's take the Dirichlet character chi, multiply both sides by chi of V bar and sum over V mod L, and you get this formula here. And most importantly, on the right-hand side, you see what you have is essentially a formation of a Gauss sum. Now you have to worry about whether L divides N or L doesn't divide N, but the point is if L divides N, then this inner sum is 0, so we can ignore it. So L doesn't divide N. And then what I have is really a Gauss sum shifted by what? Remember, I have V here and NV here, so it's going to introduce a chi of N. And that's exactly what happens. You get a Gauss sum and you get a chi of N to the S minus 1 e to the 2 pi n Z. Okay, so this is the usual Gauss sum. And so yeah, so on the left-hand side, it looks like this. Yeah. Now replace Z by AZ plus B over CZ plus D for some ABCD in SL2Z, and multiply by CZ plus D to the minus K. and sum over A, B, C, D in cosets for gamma infinity. Gamma infinity means one, the stabilizer at I infinity, 1 n 0 1, and what you get is a sum like this. Okay, so let's see, did I do this correctly? Yes, because I've replaced z by az plus b over cz plus d, e over l plus n, and I have multiplied by cz plus minus d to the k, and I'm subnumbering this. So I get the left-hand side, and what do I get on the right-hand side? This part comes out still, and I have the chi of n to the s minus 1, but then inside here, what I get is the Poincare series. Okay. So the inner sum is the Poincare series. So unfolding, so here I have Poincare series, and I have sort of some Dirichlet series. There's the coefficients here. Now here, if I unpack this, going unfold it rather, SL to Z mod gamma infinity, and then summing over n, I can put that all together. I get this. Just A, B, C, D, and SL to Z, CZ plus D to the minus K, V mod L, like this. And on the right-hand side, I get this. Here's my Poincare series. Now, the Poincare series has a spectral decomposition in terms of the Fs, as I already said. In terms, coefficients involve the Fourier coefficients of F. And therefore, the right-hand side is, you see, let's see, I put this here. Yeah, I have here the L function of F twisted by chi at k minus s. And here's the inner product, here's the inner product times f of z. Okay. And now if you apply the functional equation, I can replace this k minus s with s. And I will end up with the following spectral decomposition, namely R, this twisted version of the Conan kernel function looks like this. It's basically the sum of the L functions times f. Okay. Now, if I look at now what's the Fourier expansion, now that's a lot more. It's a lot more complicated. Not so complicated. It's just a little bit messy. I get a big sum. I get some terms that are easy to state. Is the gamma function chi, something involving Gauss sums and so on. But then I get some infinite sum involving hypergeometric functions. Okay. And so when I put this all together, both sides, what I get is that this Fourier coefficient a k l chi s n, I can relate it to some average of L function values. Okay. Now multiply by chi and average over chi, both sides. On the right hand side, you're going to get sums involving this kind of thing. Chi of n times LF chi bar s. Now what's in on the left hand side, you'll get these average chi averages of chi twisted averages of this first Fourier coefficient. Now what's interesting is these sums we studied a long time ago. There's earlier work of Luo and Ramakrishnan on quadratic twists, but at that time I was looking at not quadratic twists, but general twists. And these things have a kind of weird inversion property. Namely, if I look at LF chi bar s multiplied by chi of n and average over chi average, so 1 over phi of L, you essentially pick up the nth Fourier coefficient with an explicit error. Let me make this intuitive. This is sort of a striking formula, very striking formula. But so let me make it intuitive to you why you expect that. It's I completely give credit to Luo and Ramakrishna who had the insight to know these kind of things could happen. They, of course, were focused on quadratic twists and trying to recover an L function, I think, from a cusp form from its L function special values. This observation is when if you don't do quadratic twists, but Dirichlet twists, then you get this thing. And in fact, it turns out this is somewhat easier to do. So intuitively, see what's happening is when you have a Dirichlet series, a good Dirichlet series, functional equation, then you can essentially, not exactly, but sort of, you can approximate it by the terms which go up to square root of the conductor, roughly. That comes from something called the approximate functional equation. So f is on SL to Z, so its level is 1, and I've twisted by character mod L. So the level of this thing is on L squared. So the conductor is like L squared. So I should be able to approximate by sum of roughly length L. And so it's roughly speaking, it's going from M up to L, whatever it's sort of like truncating the sum at L. I'm saying it's sort of like, because if you do this properly, you'll get another sum, which comes from the flip side of the functional equation. But it's intuitively, this is the way to think about it. Okay, so now if I take this and multiply by chi and average over chi, what happens? What happens is, well, if I multiply by chi and average over chi, it's just an inner sum. It's only going to pick up when m is congruent to, if I multiply by chi of n and average over chi, it'll pick up only those m's which are m is congruent to n mod L. But you see, my m is less than L, so to be congruent means it's equal. So I pick up, and remember what I'm doing here. I'm thinking of L as going to infinity. Okay, so I'm given an n, and I'm thinking of L as going to infinity. Okay, so I pick up A of n, and so that's how to see this this statement of why it's intuitively plausible. Okay, so what you do then with this, now you form an appropriate linear combination of the right hand side, and you get the first Fourier coefficient of p sub n. So remember, you have, let's go back here, way back. The first calculation I did, let's see, where is it? We observed that let's see. Did I say it here? Maybe I didn't say it. Yeah, okay, so this is the sum. And on the one hand, I have written it in terms of Poincare series, where somewhere here. Yes, here. Essentially, we have before I replaced the Poincare series with this decomposition, I got it in terms of Poincare series. And now what I'm going to do is I'm going to compare the first Fourier coefficient on both sides. And what's going to happen on the left-hand side is I'm going to get essentially the first Fourier coefficient on the Poincare series. And on the right-hand side, I'm going to get these expressions that I just wrote down here. So if I'm saying for appropriate linear combination on the right-hand side, we get the first Fourier coefficient of the Poincare series. And then you can show that it's not zero by showing that a linear combination of these terms here, AK, what I call AKL chi half, this thing at the center, are not zero. Okay. If you do this explicitly, this is what happens. I'm sorry, but there are a lot of technical details, and I can't even say we've finished working it through, but it looks like it's working. Explicitly, what happens is you get a sum like this, and after averaging over chi, you get an expression for the nth Fourier coefficient of p sub n, the first Fourier coefficient of p sub n, as a sum of 3 terms, plus sum of 4 terms rather. And of course, the first few terms are easy enough. And in the fourth term, I told you that this is written in terms of an explicit infinite series involving hypergeometric functions. And if you use the series, you use that series decomposition, and you estimate very carefully, and then your L is still yours to choose. L is independent of everything here. Okay, L, you have to make sure all your estimates are uniform in L. You choose your L to be roughly gamma of k over 4. And when you do that, you find that this term doesn't contribute, and so you get that this left-hand side is not 0. Yeah. So that's a rough. I think all I said, lots of technical details to be checked, but the point is that's the approach we're taking, and it's looks pretty promising at the moment, but it's not all written up. I think that's about all I want to say. If you have questions, I'm happy to answer questions.
Okay, well, thank Kumar for a very nice talk. Any questions?
Yeah, great. No questions.
So maybe I'll ask a question while everyone's thinking. So if it works out, then it would show that the Poincare, for any n, the Poincare series would be non-vanishing?
No, it shows that it doesn't show all coefficients are non-vanishing, but it shows that. So remember, for each weight, I have an infinite sequence of them, right? It shows the first gamma of k over 4 of them are not 0.
I see.
Yeah. So going back to estimate yeah, I mean, it doesn't tell you anything new for the Ramanujan power function because k is 12. I mean, so it won't tell you anything more from that. But so as a function of k, as k goes to infinity, it tells you more and more of these are non-zero. Yeah. I should also point out that there is more sophisticated, more sharper version of Lamers' conjecture now known due to Atkin, conjectured by Atkin and said that not only is the function, the tau function, not vanishing, but in fact it grows, roughly speaking, like n to the 9/2 minus epsilon. So the upper bound is n to the 11/2 times the number of divisors. Actually, sorry, the upper bound is n to the 11/2 plus epsilon. And what they're saying is the lower bound should be sort of like 9/2 into the 9/2 minus epsilon. And so when the dust settles on all of this, the other thing we want to check is whether it gives us any way of saying something about lower bounds. Yeah.
If I may ask, there's an even fancier conjecture due to Maeda. About irreducibility of the Hecke polynomials. Is there any chance that some analytic approach like this would say something here?
I actually don't know. Let's see. How would we do that? Maeda's conjecture gives me the impression that it is something more amenable to approach by Chabotarov, because it's irreducibility of those polynomials, right? So you want somehow the Hecke coefficients to be a single coefficient to generate as big a field as it could.
Right. Not only is it non-zero, but it's
right. But somehow it is yeah. So how do you refine or generalize being non-zero? You can either say it's the Archimedean sense, it's big, or you can say it's in an arithmetic sense, it's big because it generates a field of large degree. And I don't know how to involve the degree of the field. It's possible. Maybe one looks at conjugates of these. It's a really good question. I don't know. I don't know the answer. It's a good question.
Okay. Just a thought that popped into my.
That's a good question. Thank you.
Kumar.
Yeah, how are you doing?
Many years ago, I think Heniard and Wigner-Ross, they gave some non-vanishing of the Poincare series.
Oh.
I mean, of course, for more general setting than for reductive groups. And I use them in one of my papers. And I wonder if some of these things can be put in more, I mean, general form,
Yeah.
They may be easier to prove rather than just trying to push them in the explicit calculations. Have you thought of something like that? Or?
Yeah, exactly. When I thought that I wanted to try to do this for GLN, but I have a feeling that you will need some of these analytic tools, and they get only harder for higher rank groups, not easier. If you look for
No, of course I get, but I mean maybe some general way of looking. I'm not saying that it will work out, but because that was general, those ideas were quite general.
That's a really good idea too. And as I said, I was hoping to look at GLN after we.
Yeah, GLN would be a good thing to do.
Yeah.
Anyway, just
yeah, that's really good. Thank you.
Poincare series. That's
everyone's favorite, I think.
That's very nice talk. Thank you.
Thank you.
If there are any other questions, we thank Kumar again.
Thank you.